Hello, good morning, or good afternoon, depending on where you are in the world right now watching this. My name is Charlotte Firth, and I am from the University of New South Wales in Sydney, Australia. And today I will be presenting this paper on behalf of all the authors involved. The name of the paper is The Development of an Anthropomorphic End Effector for Collaborative Use on a Construction Site. So basically, I might just get straight into the motivation for this research to give you guys an idea of why we would want to be developing an anthropomorphic end effector for construction. Okay, so let's start with the construction industry. So let's just quickly go over the main factors that are influencing construction in Australia right now. Um, it's one of the largest industries, employing 1.1 million Australians and generates $360 billion in revenue each year. Although this is predicted to increase as the population is increasing by 1.6% each year, and we will need to accommodate for 1.6 million residents in Sydney alone, placing pressure on the construction industry and its productivity. So with an increasing demand due to population on construction, there has been some issues at hand that will increase into the future. Since 2012, there has been a 45% decrease in apprenticeships started, which is creating a shortfall of skilled trades workers on site. Each day, there are 35 construction workers seriously injured on site, having a huge impact on productivity. The trades that are claiming the most claims for serious injuries are carpenters and joiners, who are finding they're struggling with issues with body stresses due to muscle strain or injury. In order to close this gap and improve safety on site, this research proposes the use of collaborative robots on site to carry out work that could be considered detrimental or dangerous to workers' health. In particular, we're focusing on improving end effectors for collaborative robots to improve the possibility of human and robots to work collaboratively together and in a safe environment. End effectors or end-of-arm tooling are crucial to complete any task given to a robot, and this is inclusive of construction. Most commercial end effectors are designed to be parallel grippers that can only grasp a small number of objects that do not vary in size or shape. Majority are designed with hard, rigid materials that can cause injury upon collision and have pinch points within the gripping fingers. These types of end effectors are also expensive, and they can cost up to 20% of a whole robotic system. When looking for end effectors for constructions that work alongside humans, these qualities are not desirable. Here is an example in the Coax series that is a collaborative gripper. Although it has good technology, it is still a parallel gripper that could not grip all objects found on a construction site, as tools on a construction site are different sizes, shapes, and textures, which would be difficult. So this research looks into anthropomorphic end effectors. So why anthropomorphic end effectors? Well, considering all tools on a construction site are created for the human hand, an anthropomorphic end effector would have a better grasp of these tools compared to a parallel gripper. The human hand is capable of complex tasks, whereas two-finger grippers would only be successful at mostly pick and place tools. One hybrid tool is much more cost effective than a custom end effector for every task. A lot of construction robots that have already been designed are for a singular task, whereas if you had an anthropomorphic end effector, you would be able to use that robot again and again for different tasks through all phases of construction. Another good thing at looking at soft anthropomorphic end effectors is that soft materials actually reduce the complexity in the design, as seen through multiple different soft robotic projects, and soft materials are safer for human interaction, removing pinch points and absorbing impact upon collision, which would be better for a collaborative environment between humans, reducing injury in case of collisions or if there was an accident on site. The methodology for this project took an action research frame and used iterative processes to come up with different designs. So this focused on three key areas for the end effector: material, actuation, and sensors. And each one of these areas looked for particular qualities that would be used to move forward into creating a full end effector. So for materials, one of the properties that were needed were low viscosity for pouring into molds, as some of the molds can be quite complex, a durable material that's able to flex, bend, and expand without having too much strain on the material, and it needs to be flexible for a range of movement. So this then comes into actuation, where we need a high degree of movement similar to the human hand, that's able to create a strong grip or grasp, as tools on a construction site can be quite heavy, and we wouldn't want to be dropping or causing any injuries by the end effector not being able to hold the tool. And then when looking into sensor technology, this needs to aid the intelligent gripping by understanding when an object has been picked up, and it also needs to aid a safe environment, for example, of when a human being is around, whether it needs to be in safe mode or switch off completely to avoid collisions or injury. The first stage of the design iteration process was to test a range of silicons and understand their qualities. The materials range from a Shaw harness between 0010 to Shaw A90. As discussed in the last slides, the qualities are needed from the silicon to be low viscosity to pour into molds, so all paste and brush-on forms were determined not to be suitable straight away. It needed to be durable to expand and move, and have a large range of movements similar to the human hand. There were 4 silicons that were chosen for further testing with actuation and sensors, which were the 2 Platzil gels 0030 and 0010, Transil and Moldstar 16. The next stage of the iteration process was to focus on actuation. This focused on soft robotic techniques and solutions, looking at the fingers in particular. The first group we looked at were pneumatic networks, which was a common solution for soft grippers and had been designed for robots that are designed to crawl. We used the 4 silicons that were tested before. So Platzil gel 0010 was difficult to remove from the mold, as it was too soft and stretchy and ripped when it was moved from the mold. Platzil gel 30 was the most suitable silicon, as it was able to be removed from the mold, and as seen in this video, was able to flex in a bending motion. Transil worked well, but it was not as flexible and didn't move as far. This would be more suitable as a base layer design, or in a position in the end effector that requires stability. Moldstar 16A was quite similar in the fact that it was harder than the Platzil gels and would be suitable for applications that required stability. The next actuator that was tested is a fiber reinforced actuator that has one singular large chamber. It is reinforced with fiber that can run at 1 or 2 different angles on the outer side of the silicon. The angle of these determine the movement. It can bend, twist, expand. We wanted to recreate a bending motion and mimic the human knuckle, so we changed the threading pattern from this pattern here to this pattern in this image here, which resulted in, if I show you the video here, this movement. But the movement, although showed some similarities, was too unpredictable and didn't bend enough, and we decided that this was not a suitable method of actuation for the fingers, as the movement didn't mimic the human hand. The last actuation method tested was a cable actuated finger. This experimented with Transil and Moldstar gel, but they were too rigid and did not move properly, so Platzil gel was used for the remainder of the testing. The testing used a range of different cables to see how the finger would bend. As you can see in the bottom right hand images, this uses a thick thread or a metal cable. This caused the silicon to start to collapse in on itself, as it was too flexible in comparison to the cable. When using a nylon wire or fishing line shown on the bottom left hand images, it closely mimicked the human finger and its bending process. A small example here is shown in this video. We decided to go ahead with this type of movement as it closely mimicked the human hand. So once we had decided on the type of finger and actuation that we were going to be using, we focused then on sensor technology. So today I'm just going to talk about the 2 successful sensors. So this was motion capture and the force resistor or pressure sensor. So the motion capture sensors do not work within the silicon, and they need to be placed externally on the back or the front of the hand. And the pressure sensors actually worked really well within inside the silicon. They were embedded around 2 mils deep into the silicon, and although their sensitivity was slightly reduced, they were still able to pick up any form of pressure that was put onto the silicon, and they would work quite well with inside the fingers or into the palm of the end effector at hand. So in conclusion, overall for the whole project, Platsil gel has been the most successful type of silicon, especially the 0030, especially for actuation, as it was flexible and had a large range of movement. The cable actuated system allowed the finger to have the most precise control and a stronger grip in comparison to the two other types of actuations, although at this point it's still not strong enough to hold the weight of a tool such as a hammer correctly. Transil and Moldstar 16A could be used in other sections of the end effector to provide strength and stability needed to hold the hand upright. And all sensors provided an insight in solutions for collaborative environments. The force resistor sensors were the most successful embedded in the silicon and would aid intelligent gripping. And the motion capture sensor only worked externally, but would be successful in aiding safer environments if positioned correctly on the end effector. And as you can see in the picture on the right here, with all the cable actuated fingers attached to a palm, it could hold the weight of a hammer, but was not able to hold it upright or to use it. So this will be the focus for future work, focusing on other elements as well, such as the palm could add a lot of grip strength with heavy tools. Testing sensors, especially how they work within a full system instead of in isolation, and finding the right solutions in terms of sensors for things like vibrations, and developing the entire structural element to provide further strength to the gripper, and developing a wrist and base of the end effector that holds all the motors, air compressors, and electrical equipments or requirements for this end effector down the line. So as you can see on the right, this is some of the work we've been working on since we have developed the basic knowledge. So if anyone is interested in finding out more about this research, as this was kind of the preliminary step, there has been more done since. All our contact details are down the bottom here, including the names of all the authors and our emails provided as well. Thank you so much for listening and watching.